Topic 3.9 is about inverse trigonometric functions. So we've learned about inverse functions back in chapter 2. When we did inverse functions, we switched the x and the y values and then resolved the function for y. These are functions that undo each other the way inverse operations undo each other. So inverse is addition is subtraction, inverse of multiplication is division, the inverse of an exponential is a logarithm, and trig functions all have inverses. The way that we talk about an inverse function is either in two ways, the notation I guess I should say. You either write it like this, where it looks like sine to the -1 of x, or arc sine of x. Your calculators use this notation, computers use both notations. So both of these mean the exact same thing. But you would say arc sine, or I catch myself saying inverse sine. Both of those things mean the same thing. But what's important to note about an inverse trigonometric function is that it gives you the inverse piece of information. So when you normally did sine, regular, no inverse, you put an angle measurement here, sine of theta. So maybe I asked you sine of pi over 2, and you gave me the function's value, either the y-coordinate or the x-coordinate or the ratio of the y to the x-coordinate around the unit circle. But when you do inverse trig, those switch places. This time, for inverse sine, the function value is your input, the angle measure is your output. So now, I'm not asking you for function values like 1/2 or square root 3 over 2. I'm going to be asking you to think backwards and give me the angle at any particular function value. These are inverse operations, so they switch spots. Just to start off small, we're going to write the statement sine of pi over 6 equal to 1/2, which is a true statement, in equivalent form using arc sine notation. We're going to do this two ways. First way, if we straight up use arc sine notation, that means we can say that the arc sine of something is equal to something. Inside of an arc sine should not be an angle, which means you are going to put the 1/2 inside of arc sine. That is a function value, that is not an angle. The angle measurement here is pi over 6. So that is the inverse version of sine of pi over 6 equal to 1/2. You may also see it written like this, so that's sine to the -1, which we would still pronounce as arc sine or sine inverse of 1/2 equal to pi over 6. Those are the exact same thing, just depending on the notation you use. There's no real trend on which notation is better. Calculators use the -1 sign. But because these are inverse functions, and we know things about functions, functions can't repeat their x values. And then immediately we look at these curves and we notice that these x values do repeat over and over again. So when we take the inverse function, we have to check the horizontal line test on a regular sine wave to make sure we're only picking values where we don't break the function, where the function does not repeat any x's. So notice for sine of x, right? If I were to draw a horizontal line across this, it touches obviously way more than one time on this function. This is the test we've always done for inverse functions. Does it pass the horizontal line test? And I'm telling you right now, there is an inverse sine function, so we have to restrict our domain or cut off the graph so that we don't break this graph and we pass the horizontal line test. We're going to restrict the sine function between -pi over 2 and pi over 2, which means I'm going to take this line that I wrote and I'm going to restrict it to just -pi over 2 and pi over 2. So notice, it's a little bit bold on your screen. This section right here is the section that we're allowed to use as answers for inverse sine. You will never do inverse sine of a number and answer pi. It is outside of the domain for inverse sine. We can only answer functions between -pi over 2 and pi over 2 because this itty-bitty section does not repeat any x values. So we use only this part of the function's domain for inverse sine. Now, same thing for cosine. If I look at the cosine wave and did a regular horizontal line test, it breaks the horizontal line test. So we have to chop the graph off and restrict it to only one section so that we can pass the horizontal line test. The section we're going to pick for cosine is between 0 and pi, which again, if I take my horizontal line and I erase some of it all the way up from 0 to pi, that little section of the graph does not repeat any of my y values, and we would pass the horizontal line test. So here is the only part of the cosine graph that has an inverse. Those are the only angles you'll be able to answer for me, somewhere between 0 and pi. Can't give me any negative angles, can't give me anything bigger than pi. We do this also for tangent, and we just learned about the tangent function last class. It has all of these waves. And again, if we were to draw a horizontal line right here, it would break the horizontal line test. So as a whole, tangent, unless we restrict its domain, does not have an inverse until we take this horizontal line and we restrict it again to this itty-bitty section, which ends up being the same as the sine section from negative pi over 2 to pi over 2, since that's one of the tangent waves. Now, one thing I want you to notice is that when I highlighted the sine restriction up there in red, what was the, do you notice that this was brackets? Okay, and then if we look at tangent, we change to parentheses. What does that mean about tangent? Does that domain include negative pi over 2 and pi over 2? No, because think about what tangent looks like. What's happening at negative pi over 2 and at pi over 2? What are those things called? Vertical asymptotes, the lines we get close to but never touch. If you can't touch it, it can't be that value. So for tangent, you'll never actually answer negative pi over 2 and pi over 2 because we're not actually allowed to be those functions. It's undefined there. Okay, so when I ask you to do trig backwards, to do the inverse trig, you have to remember to return a value to me on these domains only. So what that looks like, flip it over. I think it's easier to visualize this in the next image we have on our notes. If we visualize it like this, we can only answer angle measures around the unit circle that are in the shaded region for sine, cosine, and tangent in this image. So for sine, it can only be from negative pi over 2 to pi over 2. So we would answer with an angle in quadrant 1 or quadrant 4 around our unit circle. For cosine, we could only ever answer with an angle from 0 to pi. So never a negative angle, never an angle in quadrant 3, never an angle in quadrant 4. And then for tangent, like sine, it's from negative pi over 2 to pi over 2, but exclusive, meaning we can't include those quadrantial angles, negative pi over 2 and pi over 2, because of the parentheses, because of the vertical asymptotes. But, and this is different from what you've done when we did like the values from the unit circle, you will never really answer with 11 pi over 6. Don't draw this, I just want you to think. If I asked you for a value and you wanted to return an angle that was here, before today you would have called that, 11 pi over 6 or, 7 pi over 4. We can't answer those values anymore because these functions are not allowed to go all the way around the circle. Is inverse sine defined in this quadrant or this quadrant? No. So instead of doing this, we're actually just going to do this, which means you're not answering with positive angles when you're down in quadrant 4. You're going to be answering with negative angles since we're going clockwise instead of counterclockwise. So let's write a note for ourselves like that because I think that's super important. You cannot go all the way around the unit circle because the functions, we'll say inverse functions, are not defined. And specifically, none of them are defined in quadrant 3, so that full stop keeps us from going around the circle because none of them can enter quadrant 3. So we know we have to put a different idea in our head on finding these different values. As a hint for ourselves, things that I have found helpful in doing inverse trig, if you get a positive trig value or an input value that's positive for inverse sine, you're going to answer with an angle that is positive. So positive input for sine, positive output for sine. If you have a negative value for sine, your answer is going to be a negative angle. The same is true for tangent. So positive input for tangent, positive output for tangent. Negative input for tangent, negative output for tangent. Super easy on sine and tangent. Cosine, however, because we can't go to quadrant 4, we can't do negative angles. If you have a positive input for cosine, you'll have a positive output for cosine. But if you have a negative input for cosine, you're still going to have a positive output for cosine. It's just going to be one of those fraction angles like 2 pi over 3 or 3 pi over 4. Some of those quadrant 2 angles. Not a negative angle, but a quadrant 2 angle. So cosine really should be the only one that causes us to pause for a second and think outside of quadrant 1 or negative quadrant 1s. Okay, it's hard to grasp what I'm asking until I exactly ask some questions. So here's what a lot of your questions today are going to look like. It says evaluate the following expressions. Without a calculator, it's a non-calculator day. What is the arc cosine of negative root 2 over 2? Okay, let's think for a second. If this was not here, and I reversed this question to where I was asking the cosine of some angle is equal to negative root 2 over 2. You guys have this memorized. What angle would I have asked you for? Let me make this positive for a second. If it was positive root 2 over 2. Pi over 4. Okay? We know that from the hand trick, from what I've had you memorize from your tables. But if I make this negative, it's no longer going to be pi over 4 because it's in quadrant 2. What is the reference angle caused in quadrant 2? 3 pi over 4. Which means that the arc cosine of negative root 2 over 2 is 3 pi over 4. So you're thinking about trig, but backwards. Because your input is the trig value, you're giving me back the angle. So what I do when I do these problems is I switch it in my head back to regular trig, because that's the way I think easier. And I'm thinking, what angle would give me this number? Oh, it would be pi over 4 in the second quadrant, which is 3 pi over 4. For part B, what is the arc sine of negative root 3 over 2? So again, the way my brain is thinking about this is if I'm just thinking what angle normally would give me the positive root 3 over 2. I know it's negative, just stick with me. What angle would that be? Root 3 over 2.
Pi over 3.
Pi over 3. Okay, so I know it's going to be related to pi over 3 somehow, but it's negative.
7 pi over 3.
Ooh, I'm so glad you said that. 7 pi over 3 is what I would have answered at first too. But remember, 7 pi over 3 is like going all the way around like this. Can we do that anymore? You can't go all the way around the circle, so instead of going all the way around counterclockwise, let's just move a small bit clockwise, which means this is just negative pi over 3. Because we can only go the negative direction. You can't go all the way around the unit circle for sine. So again, just to write down what Sammy said, this angle would have been, oh my gosh, just lost the number, 7 pi over 3. Nope, yeah, nope, wait, 5 pi over 3. But we can't go all the way around the circle, so we just take the negative version of that angle. They may not have been the nicest explanation of this. Let's try another one. How about inverse tangent of square root of 3? So again, if I'm thinking about this problem in the regular tangent way, I would say the tangent of something, some angle, is square root of 3. What angle is that normally? Pi over 3. Now, since this is negative, it's not weird. It's just pi over 3. Okay, the whole point of this is to be able to think about trig in an inverse capacity, so that if you're given the function measure, you can give me back the angle. Okay? It's weird, I get it at first. It's going to be a struggle to get your brain to not think about going around the circle. But like I said, up here, these images will really help because I know I can't go all the way around to meet this angle, so I use its coterminal negative version that just goes down a little bit instead of all the way around. Okay, if we amp this up to like an AP level question that could possibly be on the AP test, they could just straight up ask you for some of these values like this. But example 3 is a really interesting question. It says the angle theta is in standard position. So, okay, make sure you know theta is right here. The terminal ray intersects with the unit circle at point P, whose coordinates are x, comma, y. The points P, Q, R, and S are the results of the terminal ray being reflected over the y-axis, the origin, and the x-axis respectively. For each of the following expressions, determine which labeled point intersects the terminal ray at the given angles. Okay, first of all, let's understand what's happening here. If I'm asking you in part A for inverse cosine of x, the only places that inverse cosine is defined is up here. So the only possible coordinates I could answer here are P and Q, because those are the only coordinates in the domain of inverse cosine. But since it says positive x, is this x value positive, or would this x value be positive? It would be P. And here's why, if you're not understanding what I'm saying. For coordinate point Q, since that's just the reflection of P across the y-axis, that just means we've made the x negative, and the y stays the same. It's on the same level as P, but flipped over to the negative x version. R, since it's rotated about the origin, means that it's the negative x and negative y version of P. And S is the positive x but negative y version of P. So since I asked in this first question, what is inverse cosine of x? Well, x appears here, which is at point P. My next question for you, if I ask you arc sine of negative y, there's only 2 quadrants where this can appear. Which 2 quadrants can sine appear in? Sine can only appear in quadrants 1 and 4. So which one of those has a coordinate point of negative y? S has the coordinate of negative y. So again, even though this coordinate point right here has negative y, can I answer with the R point for any of these? No, because this is going to be quadrant 3. None of them are defined in quadrant 3. Number C says cosine inverse of negative x. We're back to the blues. So cosine is defined in quadrants 1 and 2. Which coordinate point in quadrants 1 and 2 has a negative x value? Q. And last but not least, we have tangent. Ooh, interesting. Tangent is defined in which 2 quadrants? 1 and 4 again. Okay, so I have these 2 as the only options for negative y over x. Which coordinate point would give me a negative ratio if I put the coordinates on top of each other? It would be S. Because if I did the ratio from the first quadrant, they're both positive. The ratio from this fourth quadrant is negative. Again, I know it can't be Q, even though that would also give me a negative tangent value, because inverse tangent is not defined over here. We can't choose it. Inverse trig, honestly, is just going to require us to do some practice problems to make sure we can answer questions like example 2. Now, when you're doing these problems, you do not have to show me this work. This is just my thinking. If it helps you to write that down to see it the way you're probably used to seeing it right now, that's probably really helpful. But if you can go straight from here to here, that's even better.